Welcome. We have various type of convergence curve. The one that is probably the most widely used is curve between the number of iteration and the best fitness function value. So, how do we plot it? Let us say at the beginning my population was P0, right. These were the solution value of decision variable x1 and x2, right, and these are their corresponding fitness function value or objective function value. So, what we can do is we can make a plot, the x axis iteration and the y axis is the best fitness function value, right. So, among these three solutions, if we see 208 is the best solution. So, I am going to plot that particular value alone. I am not going to plot 277 or 397, only the best value in the fitness function is plotted. Right. So, then subsequent to this we perform the teacher phase, the learner phase, and at the end of iteration 1, let us say this is our population and these are their corresponding fitness function value, right. So, in this at the end of iteration 1, the least value is 116 in this, right. So, I retain the first point because it corresponds to my iteration 0, and at the end of iteration 1 I had 116. So, we have plotted that 116 and we continue doing so. So, at the end of iteration 2, let us say this is the fitness function value, the best value here is 68. So, we plot that 68 over here and then we keep doing it and say at the end of iteration 10 we have this fitness function value, right, 0 0 1. In this the least one is 0, it does not matter whether you take this 0 or this 0, right, we are not plotting the solutions, we are plotting only the fitness function value, right. So, this will look like something like this. So, this is called as the convergence curve. So, this curve shows you that as iterations progressed, how much improvement we were able to do in the objective function value. In this case, it seems to have converged to the global optima, right. So, there is not much change or at least visible change in those three values. So, this curve tells us the performance of the algorithm as iteration proceeds, how we are improving in terms of the best solution that we have. So, if you think about it, in TLBO we never eliminate a solution until we have found a better solution than that, right. So, even in teacher phase and learner phase, whenever a solution was to be included in the population, it had to meet the criteria that it is better than the solution which was used to generate the new solution, right. So, that way if you see this curve will always be monotonically decreasing. For a minimization problem, it will be monotonically decreasing, right, because we are never losing out on a good solution in favor of a bad solution. So, over a period of iteration, we may not be improving from one iteration to other iteration, the fitness function is definitely not going to deteriorate, right. So, that is called as monotonic convergence and TLBO exhibits this monotonic convergence. These are three different cases of convergence curve, right. So, in all the three cases the x axis is the iterations, right. So, and the y axis is best fitness function value obtained at that particular iteration, right. So, here as we just discussed for iteration 5, the best value obtained is this point. So, in the first case if we see, right, the values have more or less stabilized, right. So, for a large number of iteration there does not seem to be significant change, right. However, if you see in the second plot, this plot over here, if you see, it is continuously decreasing, it has not stabilized. So, if you come across this situation, that means that if you perform few more iterations, there is a likelihood, again remember there is no guarantee, there is a likelihood that you will get a better solution, right. So, here we do not say that the algorithm has converged, right. So, as you see, it is still trying to improve the fitness function value, right. So, these two cases are pretty much clear, right. So, but you can also end up in cases like this, right, wherein if you see over here, for a substantial number of iteration there is no improvement in the fitness function value, right, no observable improvement in fitness function value, but afterwards it starts decreasing. So, it is not correct to fix the number of iterations and take whatever the solution we get at the end of the iterations. It is necessary that we have a look at the convergence plot and decide whether the algorithm has converged or not. So, there is another type of convergence curve which is plotted between the number of fitness function evaluation and the best fitness function value, right. Let us say in this case the x axis is not going to be iteration, the x axis is going to be the number of functional evaluation. So, what we are trying to plot is every time I evaluate the function, what is its objective function value, that is what we are going to plot. Let us say my initial population was 5, right. So, initially I would have evaluated the objective function 5 times, right. Remember, this is not iteration, it is number of functional evaluations. So, the first time when I evaluated the fitness function value, let us say it is 8, for the second member it was 12, for the third member it was 9, for the fourth member it was 5, for the next member it was 11, and this was the initial population, right. So, now let us say solution 1 underwent teacher phase and we got a new solution which had a fitness function value of 4. Right. So, when I evaluate that fitness function value, I make note of this entry that when I evaluated the fitness function for the 6th time, we had obtained a value of 4. Right. Similarly, when it underwent student phase and it generated a new solution, the fitness function was evaluated for this new solution, let us say the fitness function is 6. So, when I evaluated the fitness function for the 7th time, right, the first 5 are the initial population size, right. So, you evaluate that even before you begin the algorithm, right. The 6th one was because the first member underwent teacher phase, so you got a new solution. So, we had to evaluate the fitness function. Similarly, the first solution underwent learner phase, we generated a new solution, we had to evaluate the fitness function of the new solution. Similarly, every time we evaluate the fitness function, right, let us say we make a note of these values. Right. Now, if we plot this, it looks something like this, right. It is scattered, we can't make much out of it. If we keep doing iterations, obviously it is going to exhibit a downward trend in a whole, but the inference is not that clear because you are plotting every functional evaluation. So, for example, let us say you have generated a solution which is actually inferior, right. So, since you evaluate the fitness function of that particular solution, you also will end up plotting it if we are going to plot between functional evaluation and fitness value, right. So, what we do is we plot the best fitness value. So, what we are saying is when I evaluated the fitness function for the first time, right, I got 8. What is the best value so far? So, that would be 8. When I evaluated the fitness function for the second time, but what is the fitness function value that I have so far, best fitness function value? So, this remains 8, right. So, let us say for the third time when we evaluate the fitness function, let us say it turns out to be 9, right. But what is the fitness function value, best fitness function value that I have? So, it is between these 3, right. So, the between these 3 is still it is 8, right. So, let us say fourth time I get a solution which has a fitness function value of 5. Right. In this case, I need to compare 8 and 5, which is better, 5 is better. So, this 8 becomes 5. Then let us say fifth time you get a objective function value of 11. So, 5 is retained, right. So, sixth time let us say we get a solution 4. So, the best we have so far is 5, but now we have received 4, right. So, we will consider the best fitness function value so far obtained is 4, right. So, we keep doing this, right. So, since we encounter a 1 over here, this becomes 1 and below this there is no value less than 1. So, it remains at 1, right. So, instead of plotting this column versus this column, what we are going to do is we are going to plot this column versus this column, right. So, that plot would look something like this. So, this is functional evaluations, right. When I evaluated the fitness function for the first time, what was the best fitness function value, right. This best fitness is important. This is not fitness value, but best fitness function value, right. So, now if you see this plot will be monotonically converging, right. So, even if I, so for example, let us say here the best solution was 4, but I encountered a solution with an objective function value of 6. So, I do not consider that because it is poorer than the best that I have so far, right. So, the convergence curve can either be between iteration and the best fitness function value of the population, right, or the convergence curve can be between functional evaluation and best fitness function. So, if you observe, you would have seen that in multiple places we had employed random numbers, right. Our initial step itself was to generate a random population. So, if 2 people are working on the same problem with the same algorithm, they might start with a different set of random numbers, right, and it is perfectly possible that both of them end up with a different result, right. So, since these are stochastic techniques, what is to be done is the algorithm on the same problem has to be run multiple times. If you run it multiple times, you are expecting that the stochasticity which is involved will be taken care of, and you will be probably towards you will be reaching the optimal solution, right. So, what is done is this curve is between iteration and best fitness function value, right, which we had first seen, right. So, for every iteration, what is the fitness function value, best fitness function value in the population. So, that is what is being plotted, iteration versus best fitness function value of the population in that particular iteration, right. So, there would be 15 convergence curve, right. So, if you remember the convergence curve, this plot is very straightforward. For one run I have one convergence curve, right. So, for 15 runs we will have 15 such curves, right. So, this shows 15 curves, right. So, each color indicates one run. So, if you observe that in this 15 runs, in one of the runs the initial population itself had a very good solution, right, because you chose it randomly. It so happened that one of the random solutions which you generated is actually closer to the optima, right, whereas in one of the runs the solution, the best solution of the initial random population itself was you can say very bad, because it was above 350, right. So, for this particular run the algorithm did not have to do much, right. For the one wherein you had the initial population itself which was closer to the optima, the algorithm did not have to much, right, whereas for this particular run the algorithm had to bring it down right from some 350 plus all the way up to 0, right. So, this shows a consolidated plot of all the runs, right. So, in this case it happens that all the runs have probably converged to the same or almost equal values, right, but it is not necessary. We may end up with curves like this, wherein let us say the first run is like this, whereas the second run is like this, right. I mean you complete the number of iterations. So, this is iterations, this is again your best fitness function value, right. So, it is perfectly possible that this can happen, right. So, how do we statistically analyze this figure is that we generate a statistical table, right. So, let us say I had this 15 runs. So, that is what is in this column, all the 15 runs, and in each of the run we find out what is the best solution that was obtained, right, after the completion of the required number of iterations, right. So, let us say run 1 I had to do 10 iterations, I completed 10 iterations, and at the end of 10 iterations I have a population, the best value in the population, right. That is what we used for plotting the convergence. So, that best value is taken over here, right. Same thing for run 2, run 3 and so on. So, for example, here if you see for run 11 the algorithm had converged to a value of 4, whereas the optimal solution is 0, right. So, this can happen, right. So, now we have this vector. So, we can generate the statistical table, right. So, this is the best value. So, in best value what we do is we report the minimum value among this, since we are talking about a minimization problem. So, the best value in this is, or the minimum value in this is 0, right. So, that is what is done, right. What is the worst value, right. So, worst value if I see the maximum value, right. So, maximum value was 4, right, and the mean value is the mean of this all these numbers in the second column, the mean of that is 0.533, median is 0 and the standard deviation is 1.06. So, now this table tells us how robust is the algorithm. So, if I do multiple runs, this statistical table shows me the performance of the algorithm across the run. If the standard deviation is less, that means the algorithm is consistently converging it to the same solution, right. So, this is how a statistical table is generated for an algorithm. So far we have seen how to plot the results that we get. Let us see what would happen if I want to compare two algorithms, right. So, if I wanted to compare two algorithms, both algorithms obviously I will have to run 15 times. So, this graph is going to have 30 curves, 30 convergence curve, and it is going to be a little bit difficult to interpret things out of that. So, what we will next mean convergence curve, right. So, for mean convergence curve is plotted between the functional evaluation, right, the number of functional evaluation and the mean of best fitness function value. Let us see how it is to be calculated, right. So, let us assume that I ran the algorithm first time, right. When I executed it first time, these are the objective function values that I obtained, right. I evaluated the objective function for 16 times. So, the value obtained against each evaluation is reported here, right, and we have seen how to find out the best fitness function value till the current functional evaluation, right. So, this is the second column indicates that, right. So, first time when I evaluated 8, so I have nothing to compare, so I will take it as 8. Second time I had obtained 12, right. So, but 8 is better than 12, so the best fitness function value obtained till this functional evaluation is still 8, right. Third time I obtained the functional value to be 9, but still the one that I obtained previously is better, so I retain 8. So, we have basically seen how to do this, how to get this best value column, right. So, this I can do for the second run, right. For first run I have this column, for the second run I can generate this column, right. For the second run, when I did the first functional evaluation, I obtained a value of 12, right. So, since again I do not have anything to compare with, I take 12 as the best value. For the second functional evaluation I get a value of 8. So, since 8 is better than 12, we get 8. Third functional evaluation I get a function value of 9, but still since 8 is better I will retain 8, and so on and so forth, right. So, I can do this for run 2 as well as run 3 and run 4, right. So, now we have this thing. So, what we will do is we will find out the mean of the best value will give us 14, right. So, this is the average of the best fitness function value at functional evaluation 1. So, let us see for this, it will be this 4 plus 5 plus this 5 plus this 5, right. The average of these 4 numbers would turn out to be 4.75. So, what we are saying is when I perform the 7th functional evaluation across all the runs, the mean of the best value is 4.75. So, what we are going to do is we are going to plot this functional value and this mean of the best functional value, right. So, we will get a curve like as shown in the figure. So, this completes the mean convergence curve. So, since we have discussed few convergence curve, let us just try to consolidate it. The first one that we studied was plotting iteration versus best fitness function value. At the end of every iteration, the best value in the population is plotted, right. So, this is the convergence curve. When I do for multiple runs, this plot, the first plot will have multiple curves, that is what is shown over here, iteration and best fitness function value. Since we took 15 runs, there are 15 such curves, right. So, these two are done, right. In both of this, the x axis was iteration and the y axis was best fitness function value, right. The third plot which we saw was number of functional evaluation. So, here what we did was that if we are evaluating the objective function for the 7th time, right, at the end of 7th time you are plotting what is the best value you have obtained so far. That is what we are doing in this best fitness function value. So, till this particular evaluation, so if till this particular functional evaluation, what is the best solution you have got so far. So, that is what we are plotting over here, right. So, in this case, so for the till the 4th functional evaluation, the best solution that was obtained was 5. That is what the third plot shows, and this final plot is to show the mean. This plot is for one run, right, and this plot is also for one run, right. So, if I have multiple runs, I will have multiple such curves, right. So, the average of that curve is nothing but this curve. So, this takes care of multiple runs, right. So, now if I have multiple algorithms, right, I can plot multiple such curves and try to make some inferences from that plot, because this particular curve consolidates the information of all the runs for us, right. So, I do not need to worry about runs, because that information has been captured because of this mean of best fitness function value, right. So, these are the 4 types of convergence curves, right. We will come back to it in the next lecture also, right. So, over next 2 or 3 lectures you will become comfortable with the plotting of this curve and the use of this curve, right. So, let us now discuss how will we compare algorithms, right. Assume this is the statistical table of a particular algorithm. So, we have seen a few minutes back as to how to generate this statistical table, right. So, that time we have generated for only one problem. So, the same concept, if I am trying to solve 5 problems, let us say I have 5 problems, function 1, function 2, function 3, function 4, function 5, I will get one row for each problem. So, that is what we have discussed previously, right. So, we know how to get this table. Given 5 problems, the algorithm has to be run multiple times on each of the problem, and then you consolidate your results to get this statistical table, right. So, let us say I perform the same activity with another algorithm and I get a table like this. So, now we have 2 algorithms which were executed on 5 functions, same functions for a specified number of runs, right. So, now we have 2 statistical table. So, with this statistical table we would want to say which algorithm is better. In view of the nature of this course, what we will be doing is a very preliminary comparison, right. There are advanced techniques to compare these 2 tables. To begin with, let us just take the best value, right. So, for function 1, algorithm 1 as well as algorithm 2 gave the same best value, right. So, for the second function, same value. For the fourth function, it is the same value, right. For the third function, algorithm 1 was able to determine a better optimal solution than algorithm 2, because here I have 60 from algorithm 1 for function 3. Here for algorithm 2 function 3, the best value it was able to find out is 136, right. So, this is an inferior value, whereas this is a better value, right. Same thing for function 5 if we see, right. So, 235 is better than 254, right. So, I can make this conclusion, right. So, that is just the statistic, right. So, algorithm 1, algorithm 2. So, what we are saying is how many times algorithm 1 was better than algorithm 2 with respect to the best statistics, right. So, here in 2 cases, in 2 of the 5 problems, algorithm 1 was clearly better than algorithm 2, right, and algorithm 2 is not better than algorithm 1 in any of the cases. So, we have this value of 0, right. So, and in 3 cases both of them gave us identical results. So, that is what we have this striked off 26, 18, 46. So, in 3 cases it gave us identical results. So, similarly we can do for worst, right. So, worst means between 30 and 58, 30 is actually a good solution, right. So, this is doing good over here, 21 is same. So, let me just cross it, 137 is better than 141, right. So, this is, let me put a tick mark over here, 51 is actually bad, right, 50 is better. So, let me put a tick mark over here, and 250 is better, 263 is bad, right. So, with respect to the worst, in 3 cases, case 1, case 2 and case 3, in 3 cases algorithm 1 was better than algorithm 2 with respect to the worst, and in one case they had identical value, because here also we have for function 2 we have a value of 21, as well as in function 2 for algorithm 2 also we had a value of 21. So, now we can also do the same thing for with respect to mean, right. So, for all the 5 problems the mean is better for algorithm 1. So, 27.2, 43.4, 18.12, 20.6, 120.68, 139, 47.24, 48.4, 239.24 is better than 259, right. So, in all the 5 cases algorithm 1 is better than algorithm 2 with respect to mean, right. Similarly, you can do it for median, right. So, median also if we see 28 is better than 57, 18 is better than 21, 131 is better than 139, 47 is better than 48, and 238 is better than 259. So, in all these 5 cases algorithm 1 outperformed algorithm 2, right. So, this table tells how algorithm 1 is better than algorithm 2 from the first column, right. The second column says that how in how many of the cases was algorithm 2 better than algorithm 1, right, and the third column says in how many cases they gave identical results, right. So, similarly we can do it with respect to the standard deviation, right. So, standard deviation if we see for these 2 first problems algorithm 1 has a lower standard deviation, whereas for these 3 problems algorithm 2 has a better standard deviation, right. So, the sum of all these rows would turn out to be 5, because there are 5 problems, right. So, this table gives a comparison of both the algorithms, right. If you are not really interested in comparing the algorithms, but want to know the best fitness function value, then we can just for all the function irrespective of from which algorithm is it coming, we can find out the best solution. In this case, it happens that the best solution can be determined just by algorithm 1 with respect to the best solution, right. So, 26 for the first function, 18 for the second, 60 for the third, 46 for the fourth, and 235 for the fifth. So, if we are not necessarily interested in comparing algorithms, but are only interested in the optimal solution, then whichever algorithm gives the better solution for a particular problem, that solution is to be taken. With that, we will end this session. Thank you.